Welcome to the lesson activities for lesson 29 for college algebra. All right, so we're going to complete this table. It has columns for the logarithmic form of an equation, the exponential form of an equation, and then the solution to the equation. So to remind you, the way log form and exponential form are related, the little subscript in log form is called the base. It's also the base of the exponential form. So I'm going to have 10 as my base to the something equals something. Then logs are exponents. So when you look at the log form, what the log equals is your exponent. So we're going to have 10 to the x equals 100. So 10 to what power equals 100? And the solution would be 2. X equals 2 because 10 squared is 100. Okay, here's another one. My base is 7. The log equals the exponent, so that's 7 cubed equals x. And 7 cubed, I don't think I can do that in my head. 7 times 7 times 7. 7 cubed is 343. Okay, if I have 2 equals log base b of 25, my base is b, my exponent is 2, and it equals 25. So what squared equals 25? You could think of square rooting both sides here, and my base would have to be 5. Log base 2 of 8 equals a, so my base is 2, my exponent is a, and it equals 8. So 2 to what power gives you 8? That would be the third power. 2 cubed equals 8. And log base 10 of 10 equals x. So my base is 10, the little subscript there, that's my base. My exponent is what the log equals, so that's the x, equals the remaining 10 from the equation. So 10 to what power gives you 10? Well, that would be the first power, x equals 1. Now, e is my base, the little subscript is my base, the exponent is the x, because the log equals the exponent, and that equals the remaining number in the equation e. E to what power equals e? Well, this is very similar to the last one, e to the first power equals e. And now I have my base is 27, my exponent is x, and that equals 3. So 27 to what power equals 3? So you might not know that one off the top of your head. It's not 1 or 2 or 3 because if you raise 27 to the first, you get 27. 27 squared is 27 times 27. That's way bigger than 3. So we could try negative exponents or fractional exponents, right? So let's see, what's 27 to the negative 1? That's way too small. That's going to give me little decimals. What if I do to the 1/2? 5. Oh, that's closer. So 3 times 3 times 3 is 27. So maybe it's the cube root of 27. So that would be the 1/3. 27 raised to the 1/3 gives me 3. So x is 1/3 power. So there's a little trial and error there to figure out that the exponent that you raise 27 to make 3 is 1/3. All right, so for the rest of this table, we're going the opposite direction. We're given the exponential equation. We want to change it to a log equation and find the solution. All right, so I have 6 to the x equals 1 over 36. So 6 is the base, so I'm going to have log base 6. The log equals the exponent, so my exponent is x. And then the remaining number has to go here, 1 over 36. Log base 6 of 1 over 36 equals x. So what do you raise 6 to make 1 over 36? Well, 6 to the 2 would give you 36. To make 1 over, you'd have to use a negative exponent. So x would have to be negative 2 there. 6 to the negative 2 would be 1 over 6 squared. or 1 over 36. All right, b to the x equals 1. So my base is b, so I have log base b. The log always equals the exponent, so I have equals x. And then 1, the remaining number goes there. Log base b of 1 equals x. Or b to what power gives you 1? You have to remember that raising anything to the 0 power gives you 1. All right, 2 cubed equals x. So log, my base is 2, my exponent is 3, the x goes with the log. Log base 2 of x equals 3. In exponential form says x equals 2 cubed, which means x equals 8. 2 times 2 times 2. All right, if e to the first equals x, I have log, my base is e. It has to equal the exponent, which is 1. So log base e of x equals 1. E to the first equals what? X equals e. All right, b squared equals 36. So my base is b. So I have log base b. My exponent is 2. Your log always equals your exponent. And then 36. Log base b of 36 equals 2 is equivalent to asking b to what power gives you, I'm sorry, b squared equals 36. So what squared gives you 36? That would be 6. b equals 6. All right, so now we're going to try to evaluate some logarithms mentally without using a calculator. We're going to mentally convert these logs to exponential questions, right? So log base 10 of 100 equals what? Is asking 10 to what power gives you 100? Okay, 10 to what power gives you 100? Oh, 10 squared gives you 100. So the answer is 2. 10 to what power gives you 1,000? 10 to the third power. 5 to what power is 125? That would be 3. 5 to the third is 125. 5 to what power gives you 25? The second power. 5 to what power gives you 5? 1. 5 to what power gives you 1? Well, to get 1 as the answer to an exponential equation, the exponent would have to be 0. Anything to the 0 gives you 1. 5 to the 0 is 1. 5 to what power gives you 1 over 25? Well, 5 squared is 25, but I want 1 over 25, so it's going to have to be the negative 2 power. And 10 to what power gives you 0.01, or 1 over 100? Okay, so 10 to the 2 would be 100, but I want it to be 1 over, so it's negative 2. 25 to what power gives you 5? So the square root of 25 is 5. So if I want to think of that as an exponent, it would be the 1/2 power. 25 to the 1/2 is the same thing as the square root of 25, which is 5. 8 to what power gives you 2? 8 to what power gives you 2? Well, the cube root of 8 is 2. So if I write that as a fractional exponent, it's 1/3. 8 to the 1/3 gives you 2. And if you need some help with a calculator, if you don't know these things off the top of your head, you can do a little trial and error, right? You can say, well, it can't be 8 to the first, right? Because that's 8, and 8 squared is going to be 64. So it's going to be smaller than 1. 8 to the 0 is 1, so it can't be 0. It has to be less than 0. 8 to the negative 1 is an 1/8, which is too small because I need it to come out to 2. So you start trying fractions. You might do 8 to the 1/2, and you'd say 2.8. Oh, that's a little bit too big. Let's change that exponent a little bit. 8 to the 1/3. There it is, 2. So some of these that you might not be quite as familiar with, you can do with trial and error. But looking at k, I want to know 4 to what power gives you 4 to the 1/2 power. This is like asking what is the name of the boy named George, right? So 4 to what power gives you 4 to the 1/2? The 1/2. 2 to what power gives you 2 to the -5? The -5. 7 to what power gives you 7? That would be the first power. 7 to the 1 is 7. 3 to the 1 is 3. 7 to what power is 1? The 0 power. 3 to what power is 1? Also the 0 power. 2 to the log base 2 of 8. So let's do log base 2 of 8 separately, right? Log base 2 of 8. I'm going to do that in my head. 2 to what power gives me 8? That would be 3. Okay, so log base 2 of 8 is actually 3. So then this is 2 cubed, which is 8. So 2 to the log base 2 of 8 is 8. 3 to the log base 3 of 9. Well, let's just look at the exponent, right? Log base 3 of 9 equals, that's saying 3 to what power gives you 9? So that's 2. So log base 3 of 9 is actually 2. So this says 3 squared equals 9. So when I read this all out at the end, it says 3 to the log base 3 of 9 is 9. Let's see if we can see the pattern here. So 5 to the log base 5 of 1 should be 1. And 10 to the log base 10 of 100 should be 100. Let's just quickly check it. Like, I'm just going to do this exponent. 10 to what power is 100? The 2. 10 squared is 100. Checks. All right, so we saw some patterns in this table. See if we can generalize. Log base b of b. So that looks like log base b of b. We did that one. That one and that one are all log base b of b, right? Log base 7 of 7, log base 5 of 5, log base 3 of 3, those are always 1 because they're asking you b to what power gives you b. So it's the first, no matter what b is. Log base b of b to the x. So this is this last row of the table here. Oh, sorry, no, it's not. Log base b of b to the x. Some of those that we did are that one and that one. Those are the ones that look like, what is the name of the boy named George, right? What power do you raise b to get b to the x? The x power. Log base b of 1. So we did several that looked like that. Log base b of 1 would be like that one and that one and that one. They're always 0 because b to the 0 is 1. And then b to the log base b of x, that's the last row here, and it always comes out to x. Because exponents and logs are inverse functions, so you get the round trip. B to the log base b of x, the x comes out. So logs with special bases. We have the common log, which is log base 10. So whenever you don't see a base written, there's a little invisible 10 there. And then the natural log is log base e. So in the previous activities, we just kept writing log base e, but the shorthand for that is ln of x. It stands for log naturel, which is the way you would say that in French, the natural log. So these two special bases are the only two log buttons on your calculator. Okay, so if I look at my graphing calculator here, we've got a log button along the left right here. And then we have the ln button right underneath it. So those are the only two log buttons on your calculator. So we can practice doing some of these by hand and we can check with the calculator. So log of 1,000, right? There's a little base 10 there. A little hidden base 10 equals what? 10 to what power gives you 1,000? The third power. So let's just verify on the calculator that it also thinks that the log of 1,000 is 3. It does. Okay, good. The log of 0.01, so this is a little invisible 10, equals what? 10 to what power is 0.01? Well, 0.01 is 1 over 100, so that would have to be the -2. And we can verify the log of 0.01, -2. The ln of e cubed. So ln is actually log base e of e cubed. Right, so that equals what? E to what power equals e to the third power? Well, that would be 3. What is the name of the boy named George? So let's just double check. I'm going to type in ln of e cubed. So E is a second button over ln. So you hit second ln and you get E to, and it asks what power you want. So you type in the 3. ln of E cubed is 3. The ln of 1 over E squared, well, that would be log base E of 1 over E squared equals what? So E, that's my base, to what power equals 1 over E squared, and that's the -2. E to the -2 is 1 over E squared. Verify. The ln of 1 over E squared, -2. All right, and then this last one, E, you can't be done by hand. So it's asking E to what power gives you 5, and it's going to be what you could guess and check, right? You could do say, okay, well, E to the first is 2.7. E squared is too big, 7.389. So maybe we could try like E to the 2.5. I'm sorry, I meant to do 1.5. Somewhere between 1 and 2. 4.48. We're getting closer, but rather than do guess and check, we can just use the calculator's button. The ln of 5 is 1.609. So I can check that that is actually the exponent by doing E to 1.609. I'm going to type in all these decimals. 437,912. And I get something super close to 5, and it doesn't quite hit 5 because the calculator had to chop off the decimals there. But this is approximately 1.609. Okay, graphs of log functions. So the picture below illustrates the relationship between the graph of an exponential function and its inverse function, which is a log function. So we've got in blue, we have f of x equals b to the x, and in red, we have f inverse of x, which is log base b of x. They're inverses. They undo each other, and they are mirrors over the line y equals x. So we want to answer some questions about the graph in red, just the red one, because we've studied the exponential function already. So we're going to look at this graph of the log function, and its domain, the x values that it lives on, would be 0 to infinity, and it doesn't include the 0. That's an asymptote. Its range is -infinity to infinity. Is it 1 to 1? Yes. Does it have any extrema? No. Y-intercept? None. It never touches the y-axis. It's an asymptote. X-intercept, we have one at 1, 0. It's got an asymptote on the y-axis, which is the equation x equals 0. And end behavior, we will say, as x approaches infinity, f of x approaches infinity. It grows as x goes to the right. And then as you move to the left, you can't pass the y-axis, so we could say as x approaches 0, right, as you approach the y-axis from the right, f of x approaches negative infinity. All right, so if f of x is 2 to the x, then its inverse, right? So for an exponential b to the x, its inverse is log base b of x. So if f of x is 2 to the x, then f inverse is log base 2 of x. And if f of x is 10 to the x, f inverse is log base 10, or just log x. And if f of x equals e to the x, then f inverse of x is log base e of x, or ln x. All right, I'm going to graph 3 to the x and its inverse, f inverse of x, which would be log base 3 of x on the axes. All right, so I'm going to just plot some points, x, f of x, which is 3 to the x. So let's see, I'll do -2, -1, 0, 1, 2, 3. So 3 to the -2 is a ninth, 3 to the -1 is a third, 3 to the 0 is 1, 3 to the first is 3, 3 squared is 9, and 3 cubed is 27. So I'm going to plot those points to get my graph of f of x. So I have 0, 1. -1 is about a third, and then -2 is a ninth. Super close to 0. And then 3 to the first is 3. 3 squared is 9. 3 cubed is 27. So I'll connect these with a nice smooth curve. Looks like I've got an asymptote on the x-axis. All right, and then to graph the inverse, log base 3 of x, I'll just take 3 to the x and swap the points, right? So x, f inverse, which is log base 3 of x, it's going to be take the points on 3 to the x and just reverse the coordinates. So instead of -2, 1/9, I'm going to have 1/9, -2. Instead of -1, 1/3, I'm going to have 1/3, -1. Instead of 0, 1, I'm going to have 1, 0. Instead of, oops, I plotted this wrong. That's supposed to be 1, 3. There we go. Instead of 1, 3, I'm going to have 3, 1. Instead of 2, 9, I'm going to have 9, 2. And instead of 3, 27, I'm going to have 27, 3. Because log base 3 of x is the inverse of 3 to the x. If I know how to graph 3 to the x, log base 3 of x is easy. You just swap the coordinates. So 1/9, -2 is like there. 1/3, -1 is there-ish. And I have 1, 0. Then I have 3, 1. Then 9, 2. And then 27, 3. And I'll connect those with a nice smooth curve. And I'm going to have this y-axis asymptote. And that keeps going forever. And now you can see the relationship with the reflection over the line y equals x. All right, so I have log base 2 of x graphed as a parent function down here. If you didn't know what log base 2 of x looked like, you could graph 2 to the x and then swap the coordinates. But I gave you the graph of y equals 2 to the x. And I'm going to graph some transformations of this parent function. So log base 2 of x plus 3, this plus 3 is inside the parentheses with the x, so that indicates a shift to the left 3 units. So I'm going to pick some key points here and move them each left 3 units. So there's one, go left 3, 1, 2, 3, and you land here. And then my asymptote was the y-axis. I'm going to move that left 3 and draw in a new asymptote. And then I'm going to pick some other nice key points. There's a point that's right on a grid mark. I'm going to move that left 3. 1, 2, 3. And then there's another one on a nice grid mark. Move that left 3. There's 1, 1, 2, 3. And that should be good, I think, to be able to draw a sketch of this. Just took the whole graph and shifted it left 3. All right, now I'm going to do negative log base 2 of x. So this is a negative outside the function, which means it's going to be a reflection over the y-axis. So the x-axis, reflection over the x-axis. So I'm going to pick a few key points and make the y, take the opposite of y, reflect it over the x-axis, and see what it looks like. So this point's going to stay where it is because its y-coordinate is 0. And then, let's see, this point here, that's at 1, negative a half, is going to be at 1, positive a half. So I think that this piece is going to go up like that to reflect over the axis. And then I have 2, 1 is going to become 2, negative 1. And 4, 2 is going to become 4, negative 2. 8, 3 is going to become 8, negative 3. And I think that's good to be able to draw my reflection like that. So we learned earlier today that the domain of a log function, doesn't matter the base, any base b, is a set of all positive real numbers 0 to infinity. I'll go back and show you where we did that. That was right here. We said the domain of the log function for any base is 0 to infinity. So that means that you can only plug positive numbers into a log. So whatever I put in the parentheses for the log has to be positive. So in this case, that means x would have to be bigger than 3. So my domain for my function f would be 3 to infinity. Okay, so this last problem has a lot of parts to it, but it's a good one. If you charge a laptop battery or other rechargeable battery, you will notice that the battery doesn't charge at a consistent rate. The speed at which the battery charges is proportional to the amount left to charge. So it charges much more quickly when it's empty than it does when it's nearly full. It turns out that the time it takes to charge a battery from 0% to x% is given by a log function. F of x is negative k times the ln of 1 minus x over 100. K is some positive constant that can be different based on your particular battery, like whether it's your phone or your laptop. The K will vary. And the input variable is the percent charge remaining. The output is the number of hours it takes to reach X charge. So suppose that a certain battery can be charged from 0% to 50% in 1 hour. We want to use this information to find the value of K for the battery. So 50% charge corresponds to an X value of 50, not 0.5, because they already have the over 100 in the formula. So they're telling me that F of 50, so when X is 50, it takes 1 hour to go from 0% to 50%. So F of 50, and then I'm going to plug into the formula, that's negative K times the ln, 1 minus 50 over 100. That's supposed to equal the number of hours, which we know is 1. So now I have an equation where my only unknown is K, so I can try to solve for it. So this says negative K times the ln of 1 minus a half, that's 0.5, equals 1. So the ln of 0.5 is just a number that I could have my calculator tell me. So hit the ln of 0.5. That is negative 0.693. We'll just keep 3 decimal places. So I have negative k times negative 0.693 equals 1. So the opposite of k times negative 0.693, the negatives cancel, and so I get 0.693 k equals 1, and then divide both sides by 0.693. So k is going to be 1 over 0.693. And I get 1.443. So for this particular battery, if it's your cell phone and it takes 1 hour to go from 0% to 50%, then the K value for that battery is 1.443. So let's say that that particular battery that has a K value of 1.443, we'd like to know how long it would take to reach a 75% charge, a 90% charge, 98, 99. So I'm just going to plug into this formula, but now I have a value for K there. It's 1.443. So I know that f of x is the opposite of K, so negative 1.443 times the ln of 1 minus x over 100. That's the formula they gave us. And I just threw in the value of K that I found, 1.443. So now I just want to know how long it takes to reach a 75% charge. So I'm going to do f of 75. So just type this into my calculator. So negative 1.443 times the ln of 1 minus 75 over 100. So I'm just putting in a 75 for the x there. And I get about 2 hours. Two hours. Okay, let's check for a 90% charge. So we already knew 50% takes an hour, 75% takes 2 hours. F of 90% charge. So exactly what I just did before. I'm going to use a little trick on my calculator to pull up what I typed before, and I'm going to replace the 75 with a 90. And that takes about 3.3 hours. And F of 98, how long till we get a 98% charge? Is 5.65. And F of 99, $6.65. So it takes a whole extra hour to go from 98% to 99%. It only took 1 hour to go from 0% to 50%. That's a 50% increase. And now a 1% increase also took an hour. All right, let's see. What happens if I try to use the formula to put in 100? How long till I get to a 100% charge? 100 over 100. I get a domain error because if I try to plug in 100, I would have f of, oh, whoops. I'll be writing f of 100 is negative 1.443 times the ln of 1 minus 100 over 100. But 100 over 100 is 1, so what's in this parentheses, 1 minus 1, is actually 0. But you can't take the ln of 0. You can only plug positive numbers into the ln function. So we get a domain error. You can't plug 100 in here. So that's actually an asymptote. So if I look at my graph, of f of x, at 100, I have a vertical asymptote, which suggests that you can never actually hit a 100% charge. The time just keeps increasing, increasing, but you never actually get to 100. So here's a formula, F inverse, for F inverse. Check that it really is an inverse. What does it compute? What kinds of questions could you answer? All right, so to check that it's an inverse, we have to check that we get a round trip. So let's say we know that f of 75 is about 2, right? So I want to make sure that if I plug 2 into the inverse function, what should I get? Approximately 75, right? I should get a round trip. The two functions should undo each other. So let's plug 2 into the formula for the inverse. So I have 100 times, open a parenthesis, 1 minus e to the negative x, so that's going to be negative 2, over k, and k was 1.443. Close the parenthesis. Okay, so this should give me about 75. Whoop. Oh, I only typed 10 times and not 100 times. Typo in my formula. Oops. Come back, calculator. $100 times. And there, I get very close to 75, so it works. Technically, we should check that this works for every single x. We should check that if f of x equals y, then f inverse of y should always give me x, the round trip. Or alternatively, f of f inverse of x equals f inverse of f of x equals x, that you always get the round trip. I'm not going to do it out. And any other phenomena where a value changes less and less quickly as it gets close to a certain value, I'll let you think about that on your own.